In this video, I'm going to talk about covalent bonding and ion formation in the context of the chemistry of biology. In this video, I'll be using the Bohr model to show outermost electron shells. Recall that stable atoms have a filled outer shell. In this case, with the 1s shell, a stable atom will have 2 electrons in this outer shell. That would be true for helium, which has 2 protons and 2 neutrons. That's not true for hydrogen, which just has 1 proton and 1 neutron and 1 electron. So how can an atom become more stable when it doesn't have a filled outer shell? Well, there's 2 ways to do it. One is to lose an electron and become an ion, in which case this would become hydrogen plus 1, a hydrogen ion. The other way is to share an electron. If we have 2 hydrogens here, each of which has only 1 electron in its outer shell, the 2 can share an electron. Notice now this triangle, the electron from our hydrogen on the left, is being shared with the hydrogen on the right, the circle from the electron on the hydrogen on the right. So now we have a molecule, H2, in which there's 2 hydrogens sharing an electron. Now both of them have a filled outer shell. Oxygen has 8 protons and therefore also 8 electrons. But that doesn't fill a shell. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. To fill a shell, it needs 10. So oxygen is short 2 electrons to fill its outermost ring. But if it can find partners to share electrons, then it can fill that outermost ring, which it can do with a hydrogen and a hydrogen. We now have a total of 1, 8, and 1, 10 protons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So the charges are perfectly balanced, and we wind up with a water molecule. Oxygen can also form a double bond, covalently bonding to another oxygen. I've drawn an oxygen, each with 8 protons in the middle, and each with 1, 2, 3, 4, 5, 6 outermost electrons plus the 2 more in the innermost shell. 1, 2, 3, 4, 5, 6, 7, 8 electrons. Now there's a double bond with these 2 electrons being shared and these 2 electrons being shared, and as a result, both oxygens now fill their outermost shell. I mentioned that there's another way to have a filled outer shell. Let's consider potassium, which has an atomic number 19, in other words, 19 protons, 19 plus. So that means to balance it, it should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It needs 1 additional electron. This electron is the first electron in the next shell. That means it's relatively unstable. These inner electrons all fit very nicely together in that complex structure of orbitals that keeps them all roughly equidistant from each other and minimizes their distance from the positive charge in the middle. But this electron is free to move all over the place, interacting with those electrons and interacting with any charge nearby. So in typical biological solutions, these electrons leave. That leaves potassium with only 18 electrons. Our potassium becomes K+. Because it has 1 more proton than it has electrons, it's now potassium ion. And in biological solutions, potassium is normally an ion, K+. There are other ions. Calcium has atomic number 20 plus inside, and so it has 2 electrons in the next shell. Calcium in water loses both electrons. They're not held very strongly because that outermost shell is not filled. And they can't get close enough to that positive charge. They're too strongly repelled by all these negatives. They can't get close enough to that positive charge to be held very strongly. And So calcium tends to lose 2 electrons and become calcium++, an ion.